Welcome to 5.4 Day 2, where we are using the fundamental theorem of calculus. A couple of things we've already talked about is our area and the difference between net area and total area. If you just go on your calculator and take the integral of some function, you will get the net area. That gives the positive area above the x-axis minus, or actually it's plus, the negative area below the x-axis. So you have the net area. So your net area could be a negative number. Your total area is never a negative number. So both of these can be done on your calculator. If you have total area, you put in, and don't forget you have to put an A and a B in here because that's a definite integral. So you can get them on your calculator, but when we do these problems today, you're going to be doing them by hand, taking integrals, because we need to practice that because you don't always have a calculator. So let's start with our first example. We have 3 examples. All right, make sure you read the question very carefully. Find the area. This means total area. That means we're going to, when you graph it, you will see that between 1 and 6, you have some area above the curve and some area below the curve. You need to add those 2 areas together. Now, first of all, we need to find this point where it breaks up. And you do that by taking 8 minus 4x equal to 0, and you'll find that x equals 2. That is the point where we have positive area, and then it breaks off into negative area. So what we do with this is we take the first integral, 8 minus 4x dx, and we go from 1 to 2. Then we add the absolute value of whatever, or you could say you subtract the area, whichever way you want to look at it, from 2 to 6, same function, 8 minus 4x dx. All right, so you calculate these again. Do this by hand so you make sure you get practice. The integral of 8 minus 4x is 8x minus 4 over 2x squared. Remember power rule, you add 1, divide by the 2. We're taking this from 1 to 2. If you do that, you plug in, remember, the function at 2 minus the antiderivative at 2 minus the antiderivative at 1, and you actually get a 2 when you do that. And let's look at the area under the curve from 2 to 6. When you do this, you're going to get the same antiderivative. So we could call it 8x minus 2x squared. We go from 2 to 6. Therefore, we take the absolute value of the antiderivative at 6 minus the antiderivative at 2. And that number, you should get absolute value of negative 32. Remember, you're taking a 6, plugging it into the antiderivative minus the 2 into an antiderivative, and therefore your answer is 34. If you put this in your calculator and put absolute values on it, so your calculator would look like this, 0 to 2, 8 minus 4x dx. You should get a 34. Now, the reason we don't just do it this way is because the AP test will ask you to do it on your own. Okay, you're smarter than your calculator. All right, this is the same exact thing, just a different function. We need to take 1 over x minus 1, set it equal to 0. We find out that at x equals 1, we have a 0. So we're going to have to divide this interval up from 0.5 to 1, because this is asking us for the area, which is total area. So 1 over x minus 1 dx plus the absolute value from the integral of 1 to 2, because remember this is our interval we're looking at. 1 to 2, same thing, 1 over x minus 1 dx. When you're first doing this, I would make sure you write this out carefully. All right, 1 over x, the antiderivative or integral is 1 over x minus x. We're going to take that from 0.5 to 1. So therefore, we get the antiderivative at 1 minus the antiderivative at 0.5. Again, we're going to take the antiderivative, which is the same thing, ln of x minus x from 1 to 2. So we take the antiderivative at 2 minus the antiderivative at 1 and take the absolute value of that. All right, when we do this, we have ln of 1 minus 1 minus ln of 0.5 minus 0.5. Oops, actually, I want this. ln of 0.5 minus 0.5. All right, I want that. Plus the absolute value of ln of 2 minus 2 minus ln of 1 minus 1. Okay, so I'm just giving you a little more detail on subtracting and plugging those into the antiderivative. When you get done with this, you should get a 0.5. That should be your derivative and actually your total area. Okay, next problem, or next thing is about physical applications. This is really important to understand because the AP Calculus test always gives you functions that look like this. They will look so much like this. You may have different variables and different limits of integration, but they always look like this. And what you need to know is that if you took the derivative of both sides of this equation, take the derivative of this side and the derivative of this side with respect to t, you get that the derivative of s equals f of x. All right, what that means is that this f of x is the derivative of s. All right, so often they give you this graph, f of x is drawn, then f of x is the velocity or the derivative curve. And you've always got to think like that, that function is the derivative curve. And you've got to look at what information is given and remember that. Okay, so also if you did the same thing with our velocity and position functions up here, you find that the derivative of s equals v, and the derivative of t, if you took the derivative of both sides, equals a. This is using our fundamental theorem of calculus, all right, which is what we're studying. Okay, now we're going to do one picture graphical example. Okay, so what we're given is that we're given this equation, we're given this graph, and we're also given some points on that graph to help us. But what that tells us is this is the f function, and it equals the derivative of s, okay, with respect to t. This is the derivative of s. So this is like the velocity. Okay, this is the derivative graph. All right, so the first thing that is asked is, what is the particle's velocity at t equals 3? I don't know where I got this. I'm not looking at, oh, yes, at time t equals 5. What is the velocity at t equals 5? Okay, so let me rewrite this a little bit. The velocity at 5 equals f at 5, because this f function is the velocity. Now, if you look at this point right here, I think it tells you that that point is 5, 2. All right, so 5, 2, that is what the book tells you. All right, the second question is, is the acceleration of the particle at t equals 5 positive or negative? Okay, so acceleration equals the derivative of the velocity, correct? So what they're asking is the slope of this tangent line at t equals 5 Is the slope positive or negative? Well, the slope at t equals 5 is negative. Therefore, the acceleration is negative. The next question, and this is a fun one. The position at t equals 3. Okay, the position at t equals 3. This is the derivative of S curve. So we want the position at 3, and this is the derivative curve. So we want the area under that curve at 3. So what we need to do is take the area under the curve from 0 to 3. 0 to 3 of f of t dt. That's what we're calculating. From 0 to 3, our function is a straight line. Therefore, we're going to use area, which is 1/2 base times height, because our area under this curve is a triangle. So it's equal to 1/2, the base is 3, and the height is 3 also. So our area equals 9/2. That's the answer to part C. Okay, so here's a thinking question. At what time during the first 9 seconds does S have its largest value? Well, we know at 3 it's 9/2. Now, if we count the area under the curve, it's positive all the way to 6, and then it starts becoming negative when we start taking area off our total. So at t equals 6, S is a maximum. Also, this curve goes from positive to negative. That indicates that at t equals 6, there is a maximum. Okay, question E asks, when is A equal to 0? When is A equal to 0? Well, that's the derivative of this curve. So any point that you have a horizontal tangent, you should have A equal to 0. So I would say that's at t equals 4 and t equals 7. T equals 4 and t equals 7. The acceleration is 0. There's a horizontal tangent. Acceleration is the derivative. Okay, so it's asking, when is this particle moving away from the origin and when is it moving toward the origin? And it starts at 0. So, and that's told to us right here that this position starts at t equals 0. At t equals 0, it's gaining area, so it's moving away from the origin. So from 0 to 6, it would be moving away, and then it turns back around and moves toward the origin from 6 to 9, because the area starts getting negative, so it's moving backward. And the last question says, where's the particle at t equals 9? At t equals 9, you have to add up the areas under the curve and see which one is bigger. Or you can kind of eyeball this one, because we really don't have a way for calculating, actually calculating accurately all of the areas under the curve. But the area under the curve moving away from the particle and moving forward is bigger than moving backwards. There's that bell again. So anyway, the location of the particle is on the positive side of the origin. And that is the end of our lesson for section 5.4, day 2. Very important stuff here, always seen on the AP exam. Thank you for tuning in.